All right, well, welcome everybody. So my name is Becky Seyfried. I am the Geospatial Information Librarian here at UMass Amherst. And every semester I offer workshops. Obviously now we're doing these workshops virtually. And part of that move to virtual has kind of inspired me to put my workshops online. So in the chat, you'll find a link to basically the only resource you need for this workshop. It's all like the tutorial and all of the instructions and everything we're going to go over today are there on that link. I'll be sharing my screen as we go through the material in that link and also doing some demos of how to do georeferencing. So the goal of this workshop is learning how to georeference a historical map using specifically QGIS, which is an open source desktop GIS software. And as we'll see, we can also do georeferencing in a web browser. There are some online tools, but doing it on your own computer with desktop software gives you a lot more flexibility and allows you to change a lot of the parameters and also save the files to your own computer if you plan to work with them in the future. So it's a good skill to have, especially if you're coming from, a background in history and you're going to be using historical things like that. Great, cool. So I will get started by sharing my screen, and please interrupt me if at any point, what I'm referencing isn't appearing on the screen, or if you have any questions, feel free to interrupt me. I will try to be cognizant of the chat, but if you put something in chat and I don't respond, please unmute yourself and just interrupt me because the Zoom tools kind of disappear, so I can't see them all the time. All right, so here we are. This is the main link that you need to georeference a historical map. You see our goals today are to learn how to find things to georeference online, how to actually go ahead georeferencing them using QGIS. Part of that process is going to be talking about ground control points and how you decide what's a good or high quality ground control point and what maybe isn't a good point to use. And then we'll also touch on managing data because this is a key thing. Anybody working with any kind of GIS, it's really important to learn how to manage all the data sets on your computer. So that's what we're going to talk about. I'm assuming that if you're watching this video or are attending today, you already have some grasp of GIS concepts. I'm not going to go into a lot of detail, but if you need a refresher, there's a link here to my Learn the Basics of QGIS tutorial, which is also available on the left-hand panel. And that has some units like how to get started installing QGIS on your computer, how to get familiar with the interface, some basics about GIS, and then my favorite basic kind of topic is coordinate systems. So those are all good refreshers if you need to get started somewhere. So today we are currently in the introduction. We are going to then spend a bit of time talking about the basics of georeferencing. And then, like I said, if you want to do georeferencing using an online tool, that's really all you need to get started doing georeferencing. We'll take a break and have some time for Q&A. But I'd really like to, I think the fun part of the workshop is going to be the second half, where we talk about the advanced georeferencing concepts and then how to actually do georeferencing in QGIS. And then we'll again have some time for Q&A and wrap up. But as a reminder, if you have questions, feel free to interrupt me at any time. You don't have to save them for the Q&A. And then afterwards, I'll share this link again in email, and I will post this recording here, so you'll be able to watch it later. So we can get started now with the georeferencing basics. All right. So first, we're going to go over some key terms to know, and then where you might start looking for scan maps and photos. So again, the goal of georeferencing, let's kind of step back. Let's say you have a map that is scanned, or you have an aerial photo or something like that. The goal of georeferencing is to assign coordinates to that image. And this is basically telling the computer where that image lives in the world. The goal is so that it will actually line up with any other kind of geospatial data. So maybe you have a satellite image from Google Earth and you want to overlay a historical map on it or a historical photo. And in case you haven't thought about this before, but there are lots of georeferenced images all around you. Satellite imagery that you see in Google Maps, for example, is all georeferenced in some way. There's also some other cool links that you could check out. These are two of my more favorite kind of georeferencing related projects. The Mapping Inequality Project takes historical redlining maps. If you've heard that term before, it's, you know, in the 20th century, I can't remember the organization, HOLC, what that stands for, but they created these maps to basically designate areas of different cities according to whether or not banks should lend them money. This has resulted in a lot of racial segregation policies and kind of like patterns in residential settlement. And so what the project has done is gone and georeferenced these maps. So this is Holyoke, and this is Chicopee, and these are very close to Amherst in Massachusetts. And you can see what these historical maps look like. So they've already done the georeferencing for you. Another one of my favorite examples is historical spy satellite images called the Corona satellite program. This was done by the US in I think the 60s, roundabout there. And so this particular organization at the University of Arkansas has georeferenced all of these historical images, and you can see them here. We can adjust the slider so we can kind of see what the modern landscape looks like versus the landscape as captured in the spy satellite program. And the goal of this project is more about archaeological sites. So you can see right here at the center is like a Bronze Age tell site. And you can see how much the town has kind of developed. So this is a georeferenced image. These are the kinds of things you can do with georeferenced imagery. All right, some key terms to know before we dive in. The first is the source layer. You'll see this term referenced throughout the tutorial. The source layer is the image that you want to georeference. Going back to the GIS basics, any image is inherently a raster file. So just kind of keep that in mind. Some common file types you'll see to designate these might be .tiff or .jpeg. They can be any other kind of image file, but those are some of the more common ones. If you're going to create your own source layer, let's say you have a map that you want to scan, it's a good idea to scan it at a high resolution, like 600 dpi would be a good example of a resolution to scan at. The next key term is target layer. So the target layer is an existing spatial data set that's in the correct location that you're going to use to georeference the source layer to. You can think of it like the way I kind of envision georeferencing is like taking a pin and sticking it in my source layer and then pinning it to the right place in the target layer. You're going to do this a bunch of times, and that's how the georeferencing kind of works. So what makes a good target layer? How do you decide what to use? The first thing is that it should cover the entire extent of your source layer. You don't want part of your map hanging off the target layer because you won't have anything to georeference it against. So it should really be bigger than your source layer. You could use anything. You could use another raster like a satellite image. That's a common way that people do georeferencing, but you could also use a vector data set. And we'll do that in the tutorial. We'll use a boundary of a county to help us georeference a map of that county, because the boundary of the county also appears in the map. So anything that's in the map that you want to georeference, as long as it exists in the correct location, you can use it as a target layer. Another thing to think about is the level of detail. So if you're georeferencing something in a large area, such as the state of Massachusetts, you don't really need a lot of detail in the target layer. Maybe you just need the boundary of the state. But if you're going to georeference something that's very detailed, like an aerial photo of Amherst, you might need a much more detailed image like a satellite photo, and that's going to help you do the georeferencing better. The third key term to know is ground control points, or GCPs for short. So GCPs are, as I mentioned, with the sticking a pin in one image and then sticking it into the target layer. This is what a ground control point is. You basically, during georeferencing, look at your source image, pick a point, say a road intersection, and then pick the same point in the target layer. So what makes a good GCP versus a not so good GCP? Things that are very stable over time, or that you know won't move, are the best kinds of GCPs that you can pick. So some examples would be corners of buildings, as long as you know the building hasn't been, say, demolished and rebuilt, or it hasn't like had an annex put on it, buildings can be okay. Intersections between roads are usually really good because the like center point of the intersection doesn't usually change. And railroad lines are also really stable over time. They tend not to change very much. But there are lots of things that are not so great GCPs. So examples would be like the border between a forest and a plain or cleared field. You know, that border could change over time. Trees could be cut down, trees could grow and kind of shift that border a little bit. Water bodies, the borders of water bodies are also like they fluctuate over time depending on the water level. Maybe there's coastal erosion. These are the same reasons why individual trees are not great, or edges of roads, because all of these things could change over time. And another thing to keep in mind is about the elevation of the ground control point. So if you use the roof of a skyscraper as a ground control point, it's very high off the ground. It's much more likely that the angle at which the photo was taken, if the plane was flying at a certain angle, it's going to shift where that roof of the skyscraper appears in the image. So things that have a very high elevation difference are not super great GCPs for that reason. So again, be looking for stable features that you know aren't going to change. All right, those are the key terms. That's really all you need to get started doing georeferencing. You have a source layer, a target layer, and you're adding ground control points. So the next thing to kind of talk about is where you might want to look for scan maps and photos. I have a few links here to help you get started. We're not going to look at all of them, but feel free to explore these later. I've kind of parsed these out. So we have a few government sources. These are Massachusetts specific. MassGIS Oliver is the state's kind of GIS portal, and they have so much stuff in there. Some things that are already georeferenced. They have historical aerial photos going back to the 1990s, for example, in there. And they have a lot of imagery that you could use as a target layer. The State Library of Massachusetts real estate atlases are historical kind of land parcel maps. And that's what we use in the tutorial. If you decide to do the tutorial on your own, or if you stick around for the end, we're going to use a historical image of the town of Amherst from this real estate atlases. There's also a lot of private and public collections, as well as university map collections. A lot of these already have georeferenced imagery in them. So they're a great place to look for something that's already georeferenced. But there's also a lot of maps in there that haven't been georeferenced. And so those are great places to look for, you know, sources that you could then play around with. All right, so those are kind of the basics of georeferencing. I also want to touch on using an online tool. So as I mentioned, this is an easy way to do georeferencing. You don't have to install QGIS to do it. You don't have to have any desktop software. And basically everything is happening in a web browser. So some great reasons why you might want to use an online tool. If you're not comfortable using QGIS, if you want to do the georeferencing very quickly, and if you don't plan on working with it further, you just want to look at it online, you don't need it downloaded onto your computer for further analysis. So there's two tools that I've linked to here. One is called Map Warper. It's really easy to start using. You can actually export the things you georeference and bring them into QGIS. And it is the tool that the New York Public Library uses. So for fun, we can just check out their page. So you can see this is their Map Warper. So you can actually help them by georeferencing some of the maps they have in their collection, and then they'll, you know, continue to be able to serve those up to other patrons. So you can either browse all maps or browse ones that have already been georeferenced. You'll also see this term rectified. That means the same thing, and so on. The other tool that I've seen a lot of people use is the David Rumsey Map Collection Georeferencer. It's a little bit more complex. It allows some bookmarking, and you can do, they have a cool feature where you can compare maps, which is pretty fun. But there are some limitations on what you can upload and download for free, and it's used by the British Library. So I'm just plugging libraries left and right. So you can see that this is kind of their blog write-up about it. And we have some time built in the schedule to look at one of these tools in detail. So I'm going to go ahead and use the David Rumsey Map Collection Georeferencer. I'm going to ask you for some patience because I don't use this tool very much. And I know it is constantly kind of updating. We see we're on Georeferencer version 4 now. Some cool things. It allows you to overlay historic maps, which reveals change over time. They have some new features in version 4, but this link here should always resolve to the newest version in case they come out with a new one. Okay, so this is what the interface looks like. This is just an image. You can see they have, you have the ability to save maps to a private space. There's like, this is like a transparency button, so you can drag that and kind of fade the image out. And dragging maps here into the interface will allow you to compare multiple ones. So as I said, it's a little bit more complex. But let's see if we can get started. Feel free to interrupt me with questions anytime. I have a lot of screenshots. All right. All right, so I opened the Georeferencer compare button. I guess this is going to allow us to kind of take a look at some maps together. So right now, by default, we have this California, Nevada. You can see that this has been georeferenced. You imagine that this was a scanned map at one point and somebody added ground control points to it. And we can see that the outline of California, the coastline, matches the kind of coastline as we see it in this base map or target layer. And also we kind of see these state outlines match pretty well as well. So that's a really great georeferencing job that somebody's done. So we can now kind of add other maps from the David Rumsey collection. And they've kind of filtered here some of the ones that might be interesting. And as I hover over them, we see the extent of the map. So we can see that this one's going to be a little bit bigger. And if I click it, it's now loaded it in. And I can kind of fade that out and see how it compares to the other georeferenced map. That's pretty cool. All right. I would really like to do some georeferencing. How do I do that? All right. Yeah, I think this is the right link. So on that page, I just clicked that very first button, the fixed location of a map. And we can see that there's a nice little tutorial here, which tells us how to do it. So here they're illustrating the georeferencing process. This is our target layer, which has the geospatial information in it. It's this base map. And the person is then clicking on the source layer, which is the map that they want to georeference. And in their tool, you kind of do it a little bit backwards from the QGIS version. You click the target layer first and then the source layer. And they point out here that more points improve the precision. Again, points are ground control points, and quality matters. You're looking for all of those things that make a ground control point really good. Fixed location, it hasn't changed, and is something that is not very high off the ground. So after a few points, they say that you can try the overlay button to preview the work you've done, and then you can adjust the position of the map. And clipping will apparently remove the border, which will help in the display. Okay. Awesome. So when you open up the David Rumsey Map Collection's Georeferencer, it gives you just a map, anything from their collection. I think it's also possible to search for a map and then georeference it. But this is more of like a crowdsourcing method. They'll just give you any map in their collection and ask you to georeference it, which you're kind of contributing to the overall, program of georeferencing all their works. This particular image they gave me doesn't really look like it has much of a map. I'm not sure if I zoom in, if I'll see something in there that I could georeference. Doesn't look like it. So I don't think this is georeferenceable. So I'm going to click next and hope that they give me something better. Also not georeferenceable. Let's see. Oh, this is a map. Let's see if I know where this map is. Interesting. I don't know where this map is. If anybody does, let me know. I guess there's one point here which suggests it's in China. I'm not very familiar with that region. I'm going to click next again and hope for something better. Okay, this one it looks like is somewhere in France, but I don't see anything. This is Las Vegas. This is a fun activity. Oh, I could georeference this. This one's going to be easy to georeference because it's the entire world. So you can see they've given me the kind of like center point roughly, but it's not correct because it's currently in the middle of Africa in the map, but in the scanned image, it's over by the coast of Australia. So I'm going to start placing a few points and see what we can do. At this scale, something that is covering such a large area, the kind of detail of the points doesn't need to be super precise. I don't need to be, exactly in the very right like bay of Madagascar for it to work. I could probably kind of just pick an edge and it's going to be fine. So I'm going to try that with Madagascar. I'm going to pick the top part and I will pick the top part over here. You can see that I can kind of adjust it a little bit. All right, I've got 1 point in there. We know that point 1 is incorrect, so I'm going to just delete it. And that's going to help us out a little bit. All right, so one of the first concepts, basic concepts of georeferencing is that you want to have the points be very well distributed across the map. I don't want to have 10 points just on Madagascar if the entire map is covering the world, right? So I'm going to be looking for kind of a nice distribution. I'm going to pick kind of the tip of Greenland. And you can see I can zoom in and kind of try to locate that point in roughly the same area. That's great. Let's go for maybe a corner of the map down here. It's nice to have all the corners represented. I might pick the tip of South America. Yeah, that's great. You can see I'm not terribly concerned with hyper accuracy at this scale. Maybe some in the middle of the map would be nice. So let's go for maybe somewhere near Alaska. I might pick this little jut of land. Oh, and you see now, this is with the 4th point I've added. It's now starting to predict where the point should be in the map. It can kind of figure that out based on the 3 I've already placed, and it just automatically added this one. And I can adjust it a little bit as I see fit. There we go. Okay, and now let's see if it does that again for 0.5. I'm going to add it up into this corner of the map so that it's nice and evenly distributed. So I'm looking for something over near Norway. Maybe I'll pick this part of land here. You can see it's added it again for me. That's so nice. And as I zoom in, it's hard for me to know where exactly this is. I've lost it. Trying to match it up a little bit. What I'm going to do is delete that and try it again and see if I can. Not terribly familiar with Norway's geography. I'm going to pick this bay that goes up to Oslo. Yeah, there we go. Now I can kind of see it. That looks good. All right, so now you see I've added 1, 2, 3, 4, 5 points. That's, for a standard georeferencing, all you really need is 3 for most cases. And it is no longer showing me the please add more points. So maybe we can try overlaying and seeing how it looks. So I'll click the overlay tool. It's saying I can use the shift key to toggle between them. And I can also edit the points if I need to. All right, so I'm going to hold the shift key and see what happens. All right, what do we think? I think that looks pretty good. I think that's a pretty good georeferencing job, and I'm pretty satisfied with this. So I'm going to clip the border for them. It tells you how to do this. Okay, and we're going to kind of drag it over little bit so that we're clipping out the kind of border of the map that is a little irrelevant to viewing this in a GIS interface. All right, and when I'm done, it looks like this map is finished. I will click save. Thank you. You don't need to do anything. I can now view this map or compare an overlay. I'm going to go ahead and view this map and see how it looks. You see that I clipped the border, right? So that white border is no longer present. And I can adjust the transparency up here. So there we go. It took me a couple minutes to kind of figure out the interface, but once I got started, it was pretty easy. And you could see already what georeferencing is all about, is just adding these ground control points to connect one layer to another. And yeah, you can go ahead and do this if you want to practice. This is a great place to practice adding ground control points because it's very simple and easy to use. You could also try searching the David Rumsey map collection for a map of an area you're interested in, and then trying to georeference that. All right, so that was a very quick kind of run through the basics of georeferencing and then how to use an online tool to do basic georeferencing. So I'd love to kind of stop and pause for a minute and ask if you folks have any questions. Does anyone have a particular area of the world they're interested in exploring? We could do that together. All right, if not, then I would propose that we get started with the more advanced concepts, and that will give us more time to kind of focus on the QGIS part of the demonstration. So I'll go back and share my screen again. All right. Okay, so now we can talk about more advanced concepts in georeferencing. So we kind of got through the basics and we understand what georeferencing is all about, but there's a few more detailed concepts to kind of wrap our minds around before we're going to be able to do this in desktop GIS software. So the concepts are coordinate reference systems or coordinate systems, the different transformation methods that are available, how to assess residual error in your ground control points, and then what are the different resampling methods. So we're going to talk about each of those, and then we'll be able to kind of apply them to QGIS. So coordinate reference systems are themselves, we could have a whole workshop just about coordinate reference systems. So this is something I recommended kind of refreshing before you dig into the georeferencing tutorial. So I have a link here to a unit on coordinate systems that I put together for the Learn the Basics of QGIS workshop. And so you can read all about coordinate systems here if you need to. Just a very basic refresher is that there are two kind of categories of coordinate systems. We have geographic coordinate systems, which describe three-dimensional surfaces like a globe. And the way you know it's a geographic coordinate system is that the units are degrees, and the values of those coordinates go from 0 to 90 or 0 to 180. So if you see a coordinate that is anything more than that, it is probably not a geographic coordinate system. The other kind of coordinate system are projected coordinate systems. So the reason why these exist is that people wanted to make maps which are flat, which are two-dimensional, and they're trying to map a three-dimensional surface onto them. And so we, as we say, we project them onto a two-dimensional surface. Benefits of projected coordinate systems are many. They allow you to measure distance on a flat surface because they usually are in some kind of measurable unit like feet or meters, something like that. And they also can be more accurate So a lot of like government sources are going to use projected coordinate systems because they're actually out there in the real world measuring units to lay pipelines and things like that. And so they allow local organizations and government systems to kind of create a very accurate coordinate system that describes the particular part of the world that they are in. So it's good to know that there are these two different coordinate systems. To learn more, you can check through these slides, and then I have some activities in here and how to practice in QGIS, identifying a layer's coordinate reference system, changing it for both vectors and rasters, and then finally how to change the project coordinate reference system, which is an important part of the georeferencing process. So if you need a refresher, go ahead and check that out. And we're kind of just going to wrap that up right now. So then we can get into more of the georeferencing specific advanced concepts. So the first thing to think about is the transformation methods. Transformation happens when after you've added the ground control points, the computer is basically trying to solve a mathematical problem. It has this flat map or aerial photo, and it has your ground control points. You know, you could have as few as 3. We had 5 in the example I just did. You might add as many as 20 if you want a very like hyper accurate georeferencing. So it has all of these point locations, and it knows, you know, it trusts you that what you've said is a correct ground control point is, but it now has to figure out the coordinate location of every other pixel in the map, in the scanned image. And so it uses the transformation method, basically an algorithm, to calculate the coordinate location of every other pixel in that map. The problem with this and what makes it so difficult is that no two-dimensional representation, whether it's a photo or a map, is ever 100% accurate to a 3-dimensional surface. There's always going to be some distortion in that 2-dimensional object. Maps that are historical in nature often aren't super accurate. You know, they weren't out there with the kind of technical gear we have. So, you know, borders and boundaries might not be exactly where they are today. So that's one issue. An issue of distortion that comes from aerial imagery like photographs or satellite images are that the angle at which it was taken and changes in elevation on the ground are going to show up as distortion in the image. If you can picture in your mind like what an aerial photo would look like if you have a valley on one side and a mountain on the other, how the mountain is displayed in a 2-dimensional image is going to be distorted, you know, depending on the angle the plane was at when it took that photo. So when you as the GIS user are adding ground control points, the computer doesn't know what, you know, it's not smart enough to know that this is a mountain. It just knows that the ground control points aren't lining up exactly. And so it now has to kind of figure out how to balance that out and get the best fit for the entire image. So these are the options, the transformation methods that are available in QGIS. They kind of are, as you can see, are increasing a little bit in how many ground control points are needed. They also are increasing in terms of what they're doing to manipulate the image. The most basic ones, the Helmert and the polynomial one, or we might say first order polynomial, only need a few ground control points, and all they're doing is shifting. That means taking the image exactly as it appears on your computer and moving it. They're scaling it, which means increasing it or shrinking it, and they might be rotating it. That's it. Once we start getting into the higher order transformations like polynomial 2 or second order polynomial, we start to get warping happening. And what that looks like in this cute little infographic we have here, we see the first order, all it's doing, you know, shifting, scaling, rotating. And starting with the second order polynomial, we start to get some warping. So that's when it's like, if you imagine your photo or map is like a rubber sheet, it can start to bend it in different directions. And the third order is going to add even more warping to try to fit that image to the 3-dimensional landscape in the best possible way. So going back up here, we see that To do a polynomial 2 or second order polynomial transformation, you need at least 6 ground control points. So I'm guessing the one we did in David Rumsey, since I only added 5, I think I might have, oh, there it is. I only added 5, so I'm guessing they did not apply a second order polynomial transformation. They probably did a first order. Okay. Then we have some other options that are here that are not polynomial transformations. We have a thin plate spline, which the old term for this particular transformation was rubber sheeting. I mean, that's again, if you picture that your map is a rubber sheet, that is the most akin to the metaphor I used before, where you take a pin and stick it in your rubber sheet and then stick it in the map. You imagine with this method, every ground control point, the computer is going to treat them as precisely accurate, and it's not going to change those ground control points at all, literally pinning them into the map. What's changing in this transformation is all of the pixels in between the ground control points, so they can have a lot more distortion. Your ground control points are precise and everything else is bending in order to accommodate them. But with the polynomial transformations, the approach instead is more of a global accuracy. So the computer with these ones is going to shift your ground control points a little bit. You might tell it, you know, this point is in this particular coordinate space, but the computer might shift it a little bit with the goal of maximizing the accuracy of the entire image. So these are better if you want kind of like global accuracy. You want every pixel to be the best fit. And the thin plate spline is really best if the specific ground control points you've identified have to be in the exact location where you say they are, and you're okay with there being distortion in the rest of the image. And the projective is really good for oblique aerial photos. We don't need to get into that. Just a kind of note is that other GIS software also uses transformation types. They might have slightly different names. So if you're using ArcGIS software instead, you'll see these kinds of transformation methods as well. They'll just have slightly different names. This, in fact, is an ArcGIS kind of representation. So I think these are the terms they're using. But all of that said, it's good to know that there are all of these transformation methods, but the one that I would recommend you use for maps and aerial photos is the second order polynomial, or polynomial 2. And the reason is that it is allowing for some warping, but it's not going overboard. It's not doing a lot of warping. And again, unlike the thin plate spline, it's prioritizing kind of global accuracy. So it's really good for those applications in general. So that's the one I'd recommend you use. You can always play around and try different transformations and see how it affects your image. All right, the next concept to think about is residual error. Now, again, we talked about how the computer is trying to fit the image to all of the ground control points you've identified. If you use one of those polynomial transformation methods, there's going to be some shifting of the ground control points. And this is what's called the residual error. In the QGIS interface, this they're defining as residual error, the distance in pixels from where you place the ground control point to where the software wants to put it. So in this example I have here, I am georeferencing the town of Amherst historical map, which we'll get to in the tutorial. And you see, just for fun, not shown in this map, but I clicked a ground control point somewhere up here in the map that I deliberately like mislocated, like very far apart from where it should be, because I wanted to see the effect on the overall transformation. So you see what's happened is that the computer, trying to accommodate all of the ground control points, you know, assuming that where I put them are correct, it's shifting the ground control points, and that's the red line. So the red dot is where I placed a ground control point, and the red line tells me where the computer wants to move that ground control point to in order to create the best fit for the whole map. We see also in this interface, this GCP table, so the residual value in pixels is here. So we see that we're, you know, between 30 and 200 pixels, each of those ground control points is being moved. And down at the bottom, we also see the transformation type I've selected, which is polynomial 2. And we see the mean error, so that's like the average error of all of the points, is 262 pixels, which is not great. I wouldn't recommend, like, this. There's something wrong in this georeferencing. So what I did is I went back and I turned off the faulty ground control point, that fake one I put in there. And we see now, once I uncheck it, the computer is able to disregard that ground control point and then solve that equation just with the ground control points that are turned on. And we see that all of a sudden the residual of those other pixels, the correctly placed ones, is great. I mean, it's practically zero. These numbers are very small. And that one that was my fake point, you can see, is over 2,000 pixels away from where the computer thinks it will be. We see that the mean error has been reduced to 0. So that's a much better georeferencing product. But something to keep in mind, and I have this note here, low error doesn't necessarily mean the registration is accurate. This is something you should think of as a guide. And high residual error, therefore, doesn't mean that the ground control point is incorrect. If you think back to an example where you have a mountain in half the image, you might place the ground control point in the right location, but the computer doesn't know it's a mountain, and it's going to say, hey, we have to shift a lot of the ground control points to make this fit. And so you'll see a higher residual error there. My advice would be to double check the ground control points. If you look in the table and see that a couple of your points have really high error, you can zoom into them and kind of check them out and make sure you agree that they're accurate, and then keep them. You don't have to delete something that has a high error. You can think of the error as more of a guide to help you assess the quality of the ground control points. All right. So we covered transformation methods. We covered assessing residual error. And the third major thing to think about is resampling. So resampling happens in the final stage when you have added all your ground control points, you've selected your ideal transformation method, you've checked out the residual error, everything looks good, and now you want to save a copy of that image as a georeferenced raster file. So again, this is another math problem that the computer has to solve. The way I've heard resampling described, basically you have this map that you've scanned, let's say. The raster is made up of a bunch of pixels, and the computer now has to create another copy with a set of pixels, and the pixels might not be in exactly the same location. So what it does is it creates an empty grid of pixels, and then it has to figure out what the value should be at that new pixel location. And if you imagine that a new pixel might not totally overlap an old one, it might overlap 4 pixels. How does the computer know what value to use for that pixel, that new pixel? And so there's all of these different methods for it to calculate what the new pixel value should be. The 3 most common that you'll see that are available in QGIS and other desktop software, I've put in this table. Nearest neighbor is the simplest one. It basically figures out what pixel is it overlapping the most. If it's like 80% overlapping pixel with a value of 1, it's going to adopt that value. That's it. It's going to say this new pixel has a value of 1. This is a really good method, the only method really to use if your data that you're working with is like categorical. That means that the values inside your pixels are land use types, they're categories. You could be describing them as like forest or water or something like that, because you don't want the computer to alter those values at all. The next 2 are increasing in complexity, and also that means that they're using more computational resources. They're basically averaging the pixels. So it will look at the new pixel and will say, okay, it's overlapping several pixels. I want to take an average of those pixels and calculate a new value. So this is going to create a smoother image. The linear one does this calculation on the 4 nearest pixels, and the cubic method averages the 16 nearest pixels, which means it provides a much sharper image even. It takes a lot more time for the computer to process, of course, because it's running this calculation on every pixel in the raster. These are really good for continuous data. So that could be things like elevation rasters, rainfall, where the value inside the pixel is some kind of measured number, such as like 5.5 millimeters or 251 meters above sea level. And in that case, you want the computer to calculate a new value. You want it to average everything and figure out what the value should be at that new location. It's also good for imagery because it's going to produce a sharper image. The values inside it in like a photo raster, an aerial photo, are a bunch of numbers that represent a color code, essentially. Satellite imagery might also have extra bands, we call them, which might have values that reflect like how much light vegetation is giving off. And so it is appropriate for the computer to kind of average out those pixels and come up with a new one that's kind of an average of them all. That said, you can still use nearest neighbor for satellite images and aerial photos. It's just going to create a little more blocky of an image, but it's going to be a lot faster. And for our purposes, if you're georeferencing a scanned map or a historical photo, I'd recommend trying a couple of them if you want, but starting with nearest neighbor and seeing how the result looks. The important thing to keep in mind, which resampling method should I use, is that the only restriction really is that if you have categorical data, you need to use the nearest neighbor method because you don't want any resampling to happen. Another thing you have to decide during this resampling process is what file type you want to kind of save your output as. The one that I use most common is a TIFF format. And we call a georeferenced image in this format a GeoTIFF. It's a TIFF file that has geospatial data embedded in it. And what's really handy about a GeoTIFF is that it's just a single file. It's just a TIFF file. It doesn't have any auxiliary files with it. With some of the other types, like a JPEG or an IMG file, it will create auxiliary files. If you're familiar with what a shape file looks like on your hard drive, which is the shape.shp plus a bunch of auxiliary files, it's the same. So if you wanted to share a georeferenced JPEG with somebody, you'd need to make sure that you have all of the files that go together and zip it and share it. GeoTIFFs are handy because it's just one file and you don't need to bother with all of that. So that was a lot. That's a lot of like kind of heavy advanced concepts. This is a pretty handy reference here. It's a page by Esri, which is ArcGIS company. And it's called Fundamentals of Georeferencing a Raster Dataset. It's where I got a lot of the information from here distilled down, but it's a helpful learning resource if you'd like to kind of dig more into the science behind these different concepts and like how to decide what's appropriate. All right, wow, we just covered a lot. So I'm going to stop sharing again. Do we have any questions about anything we've covered so far? Thank you for attending, patients. All right, well, I'm going to then propose we take a break. I'll reconvene at 1 o'clock and then we'll be able to spend the rest of the time on the tutorial part. We'll georeference a historical map of Amherst, and we can also maybe georeference a historical aerial photo, which would be really fun. So I'll stop the recording and resume at 1 o'clock.